Okay, while this is all loading up, I'm going to get started talking and erasing. Everybody's jotted down the project numbers. Yeah. So, I'm going to spend my 3 lectures talking about data analysis. And in the last 2 lectures, we'll be focused more on the gravitational wave side. But in this first one, I really don't want to talk much about gravitational wave data analysis. I want to talk just about data analysis, because except that it's not, at some level, all data is data. It's numbers in a computer, and you're trying to fit it with something. And so it's useful, I think, to take simpler models than what you would use to fit gravitational wave data or astrophysical populations or something like this, and fit them and think carefully about how you're doing that, so that you can kind of build sort of habits and strategy for when you tackle things with the big complicated models. It's very similar to Cole's order of magnitude calculations. You want to be able to fit the simple stuff and understand everything about the fitting process and how you did it, and then move on. And I'm going to try something different with these lectures. So if you looked at the syllabus, you saw that there were a number of links included in the PDF that Enrico posted. And I would invite you, in fact, I would like it if during this lecture there are laptops open everywhere. I'd prefer if they weren't headed to Facebook, so you're all adults, you can go where you want. But I'd like it if people followed along. So in addition to papers and references that I gave you in the syllabus, which you're welcome to read beforehand, though I will try to summarize and keep everybody moving, there's a GitHub page. So if you click on the link to GitHub, you'll see I'm going to be posting part of these lectures. I will be actively developing code in response to what you guys say, and you'll be suggesting things. When the lecture's over, I'll be pushing that code to GitHub. So it'll be there. You can grab it, you can play with it, whatever. And if you do want to follow along, there's instructions there for installing a Python stack and a program called PyStan, which is what we'll be using to do the fitting. So for people who are really into data analysis in the audience, I'm going to spend almost 0 time talking about some of the stuff that we spend most of our time worrying about, which is how, mechanically, how to do a fit. PyStan is going to be the black box that solves that problem for us. And it almost always works, except when it doesn't. And I will teach you how to tell when it's not working, but we're not going to spend a lot of time discussing how it works. That would be a topic for, years more lectures. Okay. So in particular, people are welcome to click around links. Let me make this full-sized. If you're following along and you go to the GitHub page, you can download this IPython notebook. How many people here have used IPython before? Yeah, fantastic. Okay, good. You can download this notebook and you can follow along. But we're going to start off with some board work. So I just written myself a few notes here. Okay, first, the fundamental quantity in data analysis that we deal with is a probability distribution. Okay, so probability distributions are functions, but they're special functions. If I write a probability distribution, some people will almost require that you write it this way, but if I write a probability distribution, P of x, it's a function of some x, which could be 1-dimensional, 2-dimensional, 3-dimensional. In fact, in special cases that we'll talk about on day 3, it's infinite dimensional spaces x. But it's not any function. It has 2 requirements. It has to be non-negative, and if I integrate it over all possible x's, it has to integrate to 1. These are called probability densities. If you're into differential geometry, this thing is actually an n-form. It's a differential form that you integrate up, and you can work out a lot of the seemingly complicated rules about transforming these things back and forth simply if you know differential geometry. But for right now, just remember it has to integrate to 1. So in particular, if I want to talk about the same probability distribution for a different variable, it is not equal to the probability distribution is evaluated as a corresponding x. There's an additional factor called the Jacobian. This is something to keep in mind. And you can get this if you think about the units. So 1 is a unitless thing. X is some space, it's got units, it's meters and seconds and energy and, whatever my dials read on my experiment. So in order to integrate to 1 with this dx, which carries the units of x, this has to carry units of 1 over x. And this has to carry units of 1 over y. And this takes you from units of 1 over y to units of 1 over x and makes everything work out. Okay? Everybody on board? All right. Oh, I should have said, A, I really appreciate criticism, even if it's harsh. So if I'm moving too slowly or too quickly, just shout. And B, I also really appreciate questions. So if I'm moving too quickly and you don't want to shout, slow down, ask a question. So please do interrupt. Okay. The fundamental quantities that we work with in data analysis then are these probability distributions, and in particular, there's one special one. Usually in data analysis, we have some data, and we want to fit a model to it. And the data are some numbers that come out of dials, and the model is some mathematical thing that we compute. And so there's a space of data. And there's a space of model parameters. And there is a joint distribution between them. Okay, so now in LIGO, we sample at 16 kilohertz. It's like an audio track coming out of each interferometer. So this is a high-dimensional space. If you're looking at a second of LIGO data, this is 16,000 dimensional. This is as complicated as you want to make it. Could be a numerical relativity simulation. The only thing that goes in there is the mass ratio. Okay. It could be, a more complicated approximate model. It could be a linear thing. We'll be fitting lines later. So there's 2 parameters here. There's a slope and an intercept. Okay. So this joint distribution is a really high-dimensional quantity. Usually, almost always it's high-dimensional from the data, but sometimes our models are complex as well. And there's a theorem about joint distributions that says you can write them in either of 2 decompositions. So is everybody familiar with this bar notation? How many people have seen this stuff before? Yeah, okay, great. So you can either say, I want the distribution of the data. Now this thing has different units than this. This has inverse data and inverse model units. This just has inverse data units. So I can either write it as the distribution of the data at fixed model parameters times a distribution over model parameters. Or I can write it as a distribution of model parameters at fixed data times a distribution over data. Now this is all unit-wise correct, and if you think about the rules of probability for a while, you can convince yourself that this is it's actually mathematically right, but it's at least consistent in the units. And now, this is a very useful decomposition because let's just focus right here for a minute. Statisticians have names for everything. This is called the likelihood. It asks, at fixed model parameters, what is the probability distribution over the data? Or if I plug in the data I actually have, how likely would I be to see X, Y, Z, P, and Q? That's why it gets its name, likelihood. This function usually represents, and I think in almost all good data analysis represents, a just so story. Okay? What this function is saying is if I think of the model for whatever I'm fitting as fixed, how did I get my data? And the true answer to that is, well, I spent $1 billion, I built 2 interferometers, they have all kinds of control systems in them and calibration loops and everything else, and I read out a differential, okay, that story's getting long. That's never going to work. What you have to do is tell a just so story. Are people familiar with that? These Rudyard Kipling stories, how the elephant got his trunk. This kind of thing. It's meant to explain some really complicated thing with a little cute, simplified, but hopefully realistic explanation. Okay? And that's what the likelihood does. So for example, you might say that my model is just some number x. Okay, whatever. This is my weight. Okay, I weigh x kilograms. I sit on the scale, and it gives me some number, which is related to my weight it basically takes my weight, and it adds some noise to it, which this means the noise is normally distributed. It's a Gaussian distribution with zero mean. It means the scale goes up as much as it goes down, and some width sigma. That's a just so story. Really the real story is there's levers and there's force sensors and there's all kind of, scales are complicated. Even your bathroom scale, right? It's tricky. It's digital these days too. There's an A to D conversion. It's a mess. Okay, but in the end, a sensible just so story might be it takes my weight, it fuzzes it up a little bit, and prints the number to the screen. Okay? If that's your just so story, that implies a likelihood. Okay? That's what I just did. I told you the distribution of this when I know that. It's a Gaussian with zero mean and nothing. Okay? It's done. Now we can ask, is that a good just so story? I could step on the scale many times and I could see sort of if the typical numbers scatter with this amount. But once the just so story is written down, all this math is done. Okay? This is a little harder. This is often called the prior. And this quantity, you're allowed a little bit more leeway. Some people like to talk about it as your belief about things. If it's your belief, you can believe anything you want. So you can put anything in there. That's not really quite true. It's your assumption about the model before you've seen any data. Or another way to state it is, if I took a whole bunch of data and averaged over it, right? If I just integrate out the data part here, right? I just repeat the data many times. If I integrate out the data part, distributions always integrate to 1. So this piece goes away, and what's left is here. It's your expectation for the population of thetas. Now, I'm a guy. I don't look like I'm particularly huge. I'm not particularly tall. I'm not particularly trim. I put on a little weight in the last decade. So, you might say, well, my prior is that my weight is probably somewhere between, let's say, 50 and 90 kilograms. And so you might put a Gaussian distribution or something like this, which is yet another just so story, because you don't really think that human, Western European males are Gaussian distributed between 50 and 90 kilograms, but it's probably good enough. And if you combine these just so stories, then if you ignore this piece here, which only depends on what the scale put out, what the scale put out is just some constant, right? It is what it is, it's done. Then the product of these two things is proportional to this piece, which is called the posterior. And this represents the distribution of theta given the data we've seen. So if I combine my population expectation, which is probably a just so story, and I combine my data collection just so story, then what I get is a distribution over the parameter I'm trying to uncover. You can think of this as information flow. I started knowing this, I made a measurement, and now this represents my information about theta. Okay? And our hope, or prayer if you like, is that the just so stories that we tell are extracting the information that we're actually interested in. But once I have told those stories, this is just math. Okay, now I have some function that's defined, and I just have to query it to know how much information I've got. I want to know the mean value of theta, I multiply by theta, I integrate. I want to know the median value of theta, I integrate up until I get to a half the total density. I want to know, if you want to answer questions, you just ask that, That tells you all the information you have about theta. Okay? Is everybody on board? Is this creeping along? Speeding along? Pretty good? Thumbs up if it's good? Yeah, okay, sweet. Great. Okay. Now, we come back to dimensionality. So I said, this thing could be pretty high dimensional. If it's one dimensional, game over. It's a one-dimensional function. You just plot it at a bunch of places, right? You make up some thetas and you plot this. But, typically there's like, in LIGO, for example, our canonical analysis, there's 15 dimensions in here. You might put some more in there. So you can't plot a 15-dimensional function. That's hopeless. So we need a way to summarize this. And the way that is commonly chosen, though not exclusively, is to draw samples from this distribution. It's a density on theta space. So if I draw samples from it, that means that if I look in a box here and a box there, and I count the number of samples in this box, and I count the number of samples in that box, their ratio is the ratio of the probabilities in each box. So if I have enough samples, I have all the information that there is in this function, but it's often easier to deal with samples. If I have samples and I want to know the mean value of theta, I just average them together. I don't have to integrate over 15 dimensions. I don't have to plot. If I want to know the density along one axis, let's say, I just take a histogram of the values along that axis. That's it, right? So it comes down to histogramming and summing and so on, rather than dealing with 15-dimensional functions. And so this is almost always a computational process. And PyStan is one of the programs that is optimized for doing this. And the way that you write something in PyStan follows very much what I've just described. You tell it, my data look like this. My parameter space looks like that. My model looks like this. Go. And it draws samples. Okay? All right. I'm going to stop there. There may be some things that I'll come back to theoretically. But so let's get started fitting. So if you've looked at the syllabus, there's the Bible. I like to call it the Bible of data analysis. David Hogg is a fantastic data analyst and has had a number of fantastic students. And in 2010, he got together with two of his most fantastic students and wrote the Bible, which is fitting a line to data. It's linked from the syllabus. And you wouldn't think this is hard, right? You fit a line to data. You've probably learned how to do this. It's a linear algebra problem. You take, some SVD decompositions, multiply some matrices together. It's done. What's hard? Okay, but if you really absorb everything that's in this Bible, you will be in the forefront of astronomical data analysis, because it turns out it's not easy to fit a line to data. So let's do it. I've already coded up the simplest possible fit a line to data. We'll see how that works in Stan. And then I'll let you decide which direction we generalize things, because we'll find that the just so story for the simplest picture is bad. It's no good. And along the way, we'll learn sort of how you do this kind of data analysis. Okay, so in particular, let me make that a little bit bigger. There. Okay, in particular, we're fitting a line to data. So we're going to start with a very simple just so story, which is we measure two quantities, x and y, repeatedly. And we believe that there's some underlying y truth that follows a linear relation with respect to x. Okay? Now, why would you want to do this? I don't know. We're probably cosmologists. It's really a bad idea. Okay? Things are never linear, ever. And in any case, even if they are linear, are you really interested in what the slope is? Let alone the intercept. The intercept is a real pain. Like, if this is years, and this is deaths from smoking, okay, then this quantity is the number of smokers who died when Jesus was born. That's not real, okay? So, it's worth thinking about these just so stories. But this is such a popular just so story that it's what we're going to use.
Is that your time equals 0?
That's right, yeah. When x, right? B is the value of y. Yeah. So, anyway, this stuff it's a little bit slow. And we'll talk about that as well. And in any case, do you really want the slope? Right, the slope is the rate of increase or decrease of smoking deaths per year. Is that the thing that you're looking for? I don't know. Maybe it is, but usually it's not. And certainly in physics, it's almost never the thing you're actually looking for. Okay. I just put a little rant here. So normally, Hogg's really good about this. And you all, as people who have encountered IPython and have your laptops open, I see, should be better. When you post things on the archive, please include a link to somewhere where there's machine-readable tables. You can put them on GitHub. You can stick them in Zenodo if you want a citable DOI. You can collect citations for your machine-readable tables. Okay, that's like money in the bank. For some reason, Hog didn't do it. So I use this program called Tabula, which lets you open up a PDF and select a table and dump it to data. So that's a useful thing for you guys to know about if you're not already aware of it. Okay, so anyway, I did that already. So here, let me just make sure I've got a fresh session. I'll just restart everything, load up all my favorite stuff, and we'll load up the table. And if you want to look, the table is Bible's not short, folks. Okay, there. The table has 1 through 20. It's 20 data points. It's got some x's measured. It's got some y's measured. Uncertainties in the y direction, uncertainties in the x direction, degree of correlation between the two. Forget these last two columns. They'll be better just so stories in a moment. For right now, what we're imagining is we measure x perfectly. It's like your watch. You can measure time with fantastic precision, so it just ticks off. We measure y imperfectly, and this describes the degree of uncertainty. By the way, one of the reasons why the Hog paper is the Bible is the ranty footnotes. Hog hates, and I don't particularly like either, people call these error bars. I'm not an experimentalist, so I really shouldn't speak, but I think that's kind of insulting to experimentalists, right? If there were errors, they'd fix them. These are uncertainties, right? There's some intrinsic uncertainty in what they've done. It's not a mistake. It's just what happens. Okay. Anyway, that's the if you plot these up, you'll see that this is what the data looks like. So these are the x errors and the y errors, and this is x and y. Of course, there's no units because this is a totally made-up data set, but really you should put units in as well. And if you squint at this, it'll get disconnected. If you squint at this, there we go. This could be the n-sigma relation, I guess. I don't know. It could be something. It could be something real. It kind of looks like, if you can draw a line through these points maybe, and then 1, 2, 3, 4. Those guys are just crazy. Okay, so in a minute we'll want to learn the right way to deal with the crazy data, but we're going to ignore it for the moment. So let's try. Let's just fit a line through these data points. Okay. Okay, so this is equivalent to exercise 1 in the Hog paper. And they point out you can do this analytically. It seems weird since I'm sort of I like math and I'm a theorist. I'm not actually going to do it analytically. I'm going to do it numerically, largely because very soon we will be generalizing to things you can't do analytically. So we'll build the code to do the thing simple first, and then we'll just add bolts and nuts to it. And the model that they have in mind is what I just said. There's an x true that you measure. There's a y true, which is m times x true plus b. Then you observe y with a y true plus sigma y. That should be n sigma y. Okay? So how many people here have used Stan? Carl. Bless your hearts. Oh, thanks, guys. All right, here's Stan. So I pre-wrote a Stan model. Let's make that a little bigger, too. Maybe that doesn't go bigger. That's a scary thought. How many people can read that? Wow, it's all towards the front. How'd that happen? Hang on. You know what I can do? Nope. That's not going to work either.
Apple Plus, I think, makes things bigger.
Does it?
No.
Meta Plus? No. Yeah.
You should be able to
Let's see here.
control the loop.
Oh, well, that's not helpful. All right, let me open this in a different program. Which will respond. Okay. Sorry, this won't have any syntax highlighting, but this will look a little better. There we go. Okay. This is a Stan program. and it encodes our just so story. So at the largest level, there's 3 blocks to it. There's a data block. Okay, that just says what is the space of D's? Data. In our case, there's a number of observations, and then there's a vector of x's, a vector of y's, and a vector of sigma y's. Right? That's what we've done. That's it. The next block, what is the parameter space? There's 2 parameters, a slope and an intercept. And then the model. The y's that we observed are normally distributed about m times x plus b with an uncertainty that's sigma y. That's our just so story, however ridiculous it may be. Okay? I mean, it takes some practice to read these things, but is everybody pretty much on board? Okay, sweet. So now, we tell PyStan to compile the model. Sometimes this is the longest step. It takes, 30 seconds or something. So I'm going to keep talking about what we're going to do next. So exercise 1 says, fit the data except for those 4 outlier points, which they conveniently put at the beginning. Okay, so we're going to fit, Python counts from 0. So we're going to skip 0, 1, 2, 3, and we're going to fit from 4 to the end. What was that?
Sounds like astronomy.
Yeah, no, that's right. Those points, I mean, come on, look at those guys. Clearly they're not part of the linear relation, so gone. Okay? Okay. So we're going to fit from 4 to the end. In Python, we create a little dictionary. Most people have used Python, so when I say dictionary, you're familiar with that describes our data. These names here correspond to the names we put in the Stan program. The values we put in the dictionary are, the values that are appropriate. Okay, so we put that in. Now we do the fit. Okay, so it fits and it extracts a slope. So when you get a fit object, you can plot it. You can also have it print things. And now I'm going to skip over the printed stuff and look at the plot first. All right, the slope is 2.31 or 34 or something like that. And the intercept is somewhere between minus 10 and plus 10. Okay? Great. That's exciting. I don't know really what that means because, of course, there's no units on this data. But anyway, we fit it. Let's look at a 2D distribution. So have people heard the words corner plot before? Okay, so this thing's called a corner plot. Down the, so it's a matrix. It's a lower triangular matrix. Down the axis, it contains the histograms of the one-dimensional distributions, and then on each box is the corresponding x versus y for those parameters. So in this case, you can see that m and b are highly anti-correlated. And if you think about what's happening, here we are. Here we are with our just so story of the line. If I want the line to intercept right here, I still got to hit the data, right? So if I raise the intercept, I have to lower the slope, and vice versa. So great. Okay, well that's reasonable. It's always good. If this had come out the other way, we'd worry our fit has gone off the rails, right? So we should try to understand these things. But, one thing we might like to do, and we should always do when we're doing a fit like this, so we get M's and B's, and if M meant something, right, if this was the yearly death rate from, smoking or something, then you'd now go off and publish a paper about it. But before you do that, you should always check what your model says in data space, right? Data is what you spent $1 billion to get. So let's see, now that we fit the model, what it predicts for our data. So I wrote a couple functions. This function just takes slopes and intercepts and turns them into lines. So I have correlated samples of slopes and intercepts, right? Arrays of slopes and arrays of intercepts. For each pair, I make a line. And I make another line, another line, another line, another line. And I collect all those lines, and I put them on the graph, and I plot the median value of that band and some error bands around it. And let's skip that. So, it's plotted. Okay. And then the second function is, if you remember our just so story was that out there in the universe there was a y true. And it's m times x true plus b. We measure x perfectly, So the only thing we don't know about y true is we're a little uncertain about the slope and the intercept of the line, right? So let's query our model. What is y true? Okay, let's ask that. So I wrote functions that plot both of those things. You can examine them at your leisure. So here, okay, so this plot, the little black bits are the data that we have seen before without the x error bars, because we're ignoring that part. This, it's hard to see, but this really is banded. There's a dark line in the middle that's the median line, and then there's a dark 1 sigma and light 2 sigma band. Okay, that's the central, it starts at 2.5 percentile is the lower 2 sigma limit. The 16th percentile is the 1 sigma lower limit. 50th percentile, 84th percentile, 97.5 percentile. Okay, so they're 1 and 2 sigma bands. And then the green dots, which actually show up better on this projector than they do on my screen. Can everybody see the green dots? Mm-hmm. The green dots are what our model is saying the true values of y are. Our model, if you'll excuse my Danish, is bullshit. Okay? The experimenter thinks they've measured this value with that error bar. And we're saying, no, you didn't measure that at all. Y true is right here. And look, I know it really well because I know the slope and intercept really well. Okay, if you go back to your experimenter colleagues and you say this, they're not going to be friends with you. Okay, so clearly something has fallen. Okay, but we fit the line that everybody fits. Okay, so we haven't done anything wrong. In the context of our model, this is the answer. Our model's just a bad one. All right? Does this make sense to everybody? Everybody on board? Okay, so from here, it's a choose your own adventure. Okay, so there's things we could do. We could fit all the data, including the crappy data, and ask what happens, and then what to do about it. We could improve the model. Okay, we could make it so these green points look a little more realistic. We could put priors on things, so I kind of ignored, right? My expectation here, I just swept that under the rug. I didn't do anything, so I just treated this like a constant. That means I'm agnostic about the slope from minus infinity to plus infinity. That is saying it's overwhelmingly likely that the slope is either really, really large or really, really small, not 2.3 whatever. So that prior puts a lot of weight on lines that are, almost vertical to the right, and almost vertical, sloping up but sloping down. That's probably not what you actually think lines do. Okay, so we could fix that. And then after we fit the crappy data, we could deal with outliers. So we have 3 options, basically, just the first 3. Who wants to fit the crappy data? Enrico is really excited. Only Enrico. Yeah, okay, Chris. All right. Who wants to improve the model? Sweet. Okay. Who wants better priors? Okay. Well, improve the model 1. And actually, between better priors and fit the crappy data, I'm going to choose fit the crappy data. It was pretty close. Sorry, guys. Okay, so let's improve the model. So what could we do? What's a better model than this? Feel free to just shout it out. What? Sorry?
Like a nonlinear.
Yeah, well, okay, we could put a nonlinear model in, but, when I look at this data, that's something we certainly could do. Maybe we should have that as exercise 4. But when I look at this data, it's not that the green points work somewhere, and then the black, curves away, right? That's what nonlinear would do. So my guess, it's kind of a cheating guess, but anyway, my guess is that adding a nonlinear term is not going to make the green points look more like the black and win us friends with experimenters, right?
Well, what if we say that we're not friends with experimenters? We think they underestimated their errors.
Okay. We could say that the experimenters have underestimated their error bars.
So we have,
That's right.
We now have an extra factor that's called the multiplicative factor, which multiplies all of their proofs.
That's right. Yeah. So really, quality people only go into theory, to be honest. Experiment just kind of catches the dregs, right? So let's do that. We'll call it Ilya's idiot factor. Okay, so you wanted to introduce And you said, well, they just got their sigma y's wrong, right? Right? So now this is dangerous. So before we treated the observed data, we didn't mess with it. We moved M and we moved B around to match the data, but we didn't mess with what the experimenters said. But now, Ilya, my dear friend Ilya, who no one would accuse him of lacking an ego. Ilya said he knows better. Right?
This is recorded, Bo.
Oh, yeah. I'm looking forward to it. You're in the room, dude. Are you worried it's going to get back to you? My dear friend Ilya thinks he knows better. Now, I, pretending, at least while I'm in front of you, to be a more modest person than Ilya, limited the adjustment. So in Stan, you can constrain things. So for those of you who can actually read this, I said Ilya's idiot factor is a real number. Its lower limit is 0.1. Its upper limit is 10. Okay? So I'll let the experimenter's error bars go down by, a factor of 10 and up by a factor of 10. But otherwise, if I have to expand them by a factor of 100, forget it. Okay? Everybody on board? Okay, awesome.
Do you need to provide a prior on this other than limits?
Yeah, do you want to give me a prior? What do you think it is?
I'm wondering actually, so maybe you can does 10 assume some kind of a prior if you don't provide one?
If you don't provide one, it's flat. So that's actually, it's again very pessimistic about the experimenters, right? Because there's a 10% chance their error bars were too big, and there's a 90% chance their error bars were too small because it's flat from 0 to 10.
Log or something rather than flat.
Yeah, so we can make it flat in the log. How about we do this instead? We'll give it a log normal distribution. So it peaks at 1, and it scatters typically by a factor of order 3. So that's a more optimistic assumption about the experimenters. It says really 10 is kind of like a 2, it's really a 2 sigma experimenter who's so bad. But they can easily be a factor of a few off in one way or the other. Okay? And I'm being all tongue-in-cheek about this, but I actually use these factors in my own models. Okay? It's a very common thing, and it's often the right thing. Even if you do have an observer in your group, they will tell you that they estimate, but they don't get it right. So factors of 2 are not at all uncommon. And now putting my seriousness hat on, very, very good astrophysicists can easily get the error bars wrong by a factor of 2. So that's going to compile. So what do we think is going to happen here? Yeah, well, the error bars are going to get bigger. So our slope is going to be measured less precisely. If you look at this, here's the green dot. I don't know, I take that 3, 4, 5. So, maybe if I blow up the error bars by a factor of 6 or 7 or something, I can get the green dots to match the black dots. And of course, my uncertainty on the slope and intercept is going to get worse as well, which is going to scatter the green dots around more. So this might fix everything. Okay?
This is still assuming that it's a nice, there's no systematic error that they're missing. So, you're going to get an answer, but it doesn't, unless we know the uncertainties in the experiment accurately, we don't know.
That's right.
Well, I found a systematic error when I looked at it.
Yeah, absolutely. If you want to put some systematic, actually, it's probably a useless exercise because these are just random numbers.
Yeah.
But if you did want to put a systematic error in, you could add that in as a function of x. Maybe they measure large x's particularly well, but they're poorly calibrated near x equals 10. These sorts of things. You just put in the sigmas that you want. Okay, it's EX1 data. All right, it's compiled. So now we say fit it. Or it fits something. Oh, wow. Okay, so if we look at the uncertainty on M, right? Before it was like 2.3 plus or minus 0.1. Now, this is looking pretty good. The uncertainty on the slope, it's a little bit hard to see, but, or on the intercept, rather, minus 100 to 100. It used to be 10 to 10. So things have gone up. And the idiot factor. Okay, we really think they only overestimated their error bars by a factor of 5. Or underestimated, sorry. by a factor of 5, right? That's what this peaking at 5 could have been 10, but it's more probably just 5. Okay, well that's an encouraging note on our observational colleagues.
Excuse me, what am I looking at exactly now?
Okay, yeah, I didn't describe these plots at all, did I? So on the left, for each of the parameters, the top is m, the middle is b, and the bottom is Ilya's idiot factor. This is the one-dimensional distribution of that parameter after the fit.
Okay.
So having seen the data you did, it's the information you've got about the error bar scaling and so on and so forth. This is a history, so Stan is drawing samples. And what it's actually doing is it's flying around in model space using Hamiltonian dynamics to sort of try to, zip around in such a way so it constructs a dynamical system. This is I used to be a dynamicist. These days I just do Leibniz stuff, but I used to be a dynamicist. It's really fascinating how it does this. And I'm just going to say it makes a dynamical system. It flies around in theta space in such a way that the dynamical system spends time at a location that's proportional to the posterior probability at that location. So the system sort of slows down near the peak, so it spends a long time there, and then speeds up when you're in the wings so that it zips right through the parts that are low probability. And this is a trace of where that goes in Ilya's idiot factor, in B, and in M.
Okay, so that's the way it's fitting the model.
Yeah, that's right. So on the left is that distribution, and any method would give you this if it's correct. On the right tells you the history of Stan. And in particular, if you see like a trend here, then it didn't really fly around, right? It went, so it couldn't have explored the whole distribution. So if you see a line here or some kind of trend to it, this part is junk.
Okay, so so this tells you that maybe it exists, maybe this factor actually exists, because if you put a factor that would be obviously wrong, you would get an image that...
So I think you might view this, there's this, Andrew Gelman has this thing he calls the Folk theorem, which is incorrect models are hard to fit. So at some level, yeah, if the model was completely, wildly uninformative and wrong, Stan will choke on it, and the fit will be difficult. But there are lots of wrong models that can nonetheless be successfully fit. For example, the first one we used. Right, that was totally wrong. And yet it fit just fine, and if you looked at those tracks, they look just as mixed, just as scattered. Ilya?
Yeah, just to make a comment in connection with the original question, to connect things to the stuff that Wilt had written on the right. So the plots on the left are what Wilt has called P of theta given data, so the posterior, but integrated over all of the thetas other than the one being plotted. So that's called being marginalized over all of the other parameters. So
it's M ignoring everything else.
Yeah, okay.
B ignoring everything else. Idiot factor ignoring everything else. Yeah. Statisticians have language for everything. So we don't call it integrating or ignoring. We call it marginalizing because it sounds sexy. Okay, so let's make this same plot. And now I'm doing something you shouldn't do. I'm copy-pasting. Okay. And I just called this samples. Because, that's not a name I'm going to want to use again. Oh, no, I called it samples Ilya. See, I outsmarted myself. By the way, people who don't use IPython notebooks very much, you'll note that you can hit tab, and it'll complete variable names. If you're like me and you like to save a lot of time. Ooh, hey. Okay, so the line got fatter. Oh, okay, that's appropriate. Oh, let's show one more thing, actually. So this is the plot as it was before, right? But in fact, we're claiming that it's not really good to put that little error bar, right? That's what Ilya's idiot factor does. So let's blow that up. Let's just blow it up by the mean value. Okay. looks like a nice fit. Now this, if you took this to your experimenter colleagues and you didn't tell them you'd blown their error bars up by a factor of 5, right? This is totally reasonable. And in fact, what you would tell them, okay, look, I fit this model, right? And it looks pretty linear. And it goes mostly through the data points. And now this is a clincher. This is actually deep. People don't think about this, but this is actually deep. Because I have modeled simultaneously all of these data points, and I'm asserting they lie on the line, I have actually made an improved measurement of each one. Right? I mean, if I really believe this just so story, then the real measurement is this green, not black. Okay? The fancy statistician's term for that is a hierarchical model. Okay, or a multi-level model, or a shrinkage analysis, all kinds of fun-sounding stuff. But effectively what we've done is an individual measurement has this error bar, and if you fit them without any model linking them together, you just get that. Right? That's it. But we've linked them together. We have made repeated measurements that we assert are actually coupled through this linear relationship. And that means, sort of, in a very hand-wavy sense that you can make kind of precise, you should take this error bar and reduce it by square root n. Because the fact that this measurement is what it is implies something about what this value really was. And that measurement is what it is, and so on. Okay? So you can shrink your estimates through these models. Does that make, yeah?
So in this plot, it looks like there's a 2 sigma error range above the 1 sigma, but not below. Is there a reason for that?
Yeah, that's an interesting question. It's probably a mistype. Let me see if I can fix that offline. When this is done, I'm going to do a git push, which is end of lecture, and then tonight I'll kind of go through and put a little text around stuff and clean it up so it's actually intelligible. Okay. I want to propose a slightly different model than Ilya, though. Ilya says the experimenter's screwed up. I'm going to, again, in my faux humble state here in front of the room, I'm going to say the theorist screwed up. And what happened is not that, one thing you notice, these green dots, right? They lie perfectly on the line. Right? Our assertion is still the underlying model is truly linear. Things are never linear. I want to say that the underlying model is that things lie on the line, so y true is mx true plus b plus some random scatter that picks y up and down. And people often call this intrinsic scatter, unmodeled variance, whatever you like to call it, depending on what your stats are. Okay, the point is that it's not really a line, it's a line with a little bit of fuzzy noise on it. Okay. So now, it's going to not be a good idea to have both of our guesses in there, because they're sort of degenerate with each other, right? In one case, you're kicking these points around more, and in the other case, you're kicking the green points around more. But, it depends on whether you want to blame the experimenters or the theorists. In this case, I'd say the theorists are better. So let's fit that. And this time, I'm going to call it a new file. Okay, so in this case, I'm just going to call it sigma. I'm being modest. Okay, so now, before, and we didn't have this, since we measured this perfectly, we knew exactly what that was. We didn't have to fit it at all, right? It was just m times x plus b. Once we knew m and b, we were done. But now, this is actually a parameter. Right? Even if I know m and b perfectly, I don't know what this is. So I guess we'd better introduce parameters for that. So in addition to this sigma, we have a vector of y trues. And our statement is that y true is distributed as a normal about mx's plus b with a scatter of sigma. And then we believe that the observers were right about the error bars. So the observed y's scatter about y true with sigma y's. Now, for the mathematicians in the audience, in fact, this model is actually, you can analytically integrate out the scatter if you wanted to, because you're basically convolving two Gaussians together, which is another Gaussian, so you could create a different sigma. But it's kind of fun to have Stan predict the y trues, because then it makes a cute plot as well. So let's do that. All right, so let's sample that. All right, well, that's compiling. Are there any questions? Yeah.
So how would you justify that? Adding this. For example, okay, let's say you're in the stock market, so you would say that it fluctuates.
Yeah.
Around.
So,
but in theory, you want to model something.
yeah.
And you're supposed to know your y 100% if your model is correct. But now you have added this random walk.
Yeah. Well, let me give you, so I'm going to tell you a slightly more sophisticated just so story. This is height. This is some measure of nutrition.
Okay.
Okay?
Okay, I get it.
Right? So now B
So height
is the
itself.
height of a person if you feed them Spam and nothing else. Okay? And then this is how much return you get from adding cabbage. Okay? So this is the amount of cabbage in your diet. And now I'd say, well, your height, there's a million different genes. And some of them make you a little taller, and some of them make you a little smaller. And some people run a lot and a little, and some people eat a lot and there's just billions of effects that aren't really making that much difference. I mean, it's rare to be 7 feet tall, okay? But lots of people are 6'1" or 6'2" or whatever. Sorry, I'm American with funky units. Anyway, okay, so the sum of a lot of little things that push you a little up and a little down, a little up, a little down. Doesn't matter what their distribution is, the outcome of that by the central limit theorem is a Gaussian distribution of height. So if I thought the only thing that has consistent causal effects is the amount of cabbage in an otherwise Spam diet, and then everything else just jitters you around, then, this is a pretty good model for what's going on.
Unless you're allergic to cabbage.
Yeah, that's right. So this is the issue of, sort of generalization. Is the population you're looking at the real population? Are there special outliers? How much person-to-person variance? The medical statisticians go nuts with this stuff, and justifiably so. Yeah.
Okay, but let me actually follow up your example for a moment, right? So,
Yeah.
so in your example, I'm trying to prove that there is some correlation between the height and amount of cabbage that you eat. So m is hopefully that means I will get a value of m, a posterior m that is positive and statistically significantly different from 0, right?
Yeah.
Meaning it's inconsistent with 0, and so I can tell people you should go and eat lots of cabbage and they'll be good for your height.
Actually, this kind of analysis, all you can say is cabbage eaters tend to be taller.
Okay,
You don't know which direction, like does it flow from height to cabbage or cabbage?
Okay, but right, you're right about the correlation.
Yeah.
The point, but for the sake of argument, suppose. Okay, now that it was a controlled experiment and I could feed or not feed people cabbage. Okay, now the only issue I see, however, is the following. In principle, I can choose to make my model complicate in different ways. I could add this random noise looking like this. I could add some multiplicative random noise. I could, add some sinusoidal random noise. I have lots of different choices for other factors I can add. I have one obvious constraint. The constraint is that in the end, my residuals should be consistent with the measurement errors.
Yep.
Fine, because I do believe the experimentalist.
That's right.
But do I have the risk that depending on which model I use, whether it's normal or log normal or something else over there, I may actually reach drastically different conclusions about m. In one case, I find that m is unambiguously positive. In another case, I find that m is unambiguously negative, and the fit is just as good. What do I do now?
You do science. Okay, so it will come, actually, I think tomorrow? No, Wednesday, lecture 2, maybe actually it'll be in lecture 3 that we get to it. We'll talk about how I have 2 models, I have some data, I want to know which one is better. So there are ways in which you can say, on this data set, this model is better than the other one, which you know, of course, very well, but I'm saying this for the benefit of everyone else. Sometimes those will even fall down. You'll have two models. They have very different implications about the effects of cabbage. Neither is obviously preferred by your data. And then you basically have two options. One is to be a better Rudyard Kipling than anybody else and say, because I really have this very good story for model A and not model B, I'm going to go with it. Two is to get more data. And that's it. Well, but that's science, right? When we sit here, there's a Newtonian gravitational potential. Grad squared phi is, minus 4 pi rho, okay? Or there's dynamics from GR, Einstein's equation. G mu nu is, whatever T mu, right? And both of those models are pretty darn close for the solar system. They have wildly different interpretations. But if you didn't know about the precession of Mercury, for example, you couldn't do lunar laser ranging, you couldn't time the Cassini spacecraft, you had just sort of maybe even pen and paper with your eyes, observations of the planets, they'd be equally good. And then, you could tell a just so story about GR. I don't think things should move at infinite speeds, and this Newtonian potential seems to change instantly with the mass density, and, we can do E&M, so we think special relativity is at least right. So we better, cook up a theory that respects that, and this does and that doesn't. Okay, and that's all of these things are doing science, but the data, they just aren't going to help you.
Yeah, I guess maybe to reformulate my question, the question was not so much in the where you already have those two models and you can tell they give you different predictions.
Right.
Then you know to be concerned. I guess the real problem is I only Will's idea is out there. You're going to show me some fit with this particular model. It'll look great and will be tightly constrained, let's suppose, with some positive value. We'll go home happy without even realizing, well, maybe one could have come up with a really perfectly reasonable model where M would have been well constrained to having a negative value, right? And then you don't know that actually it's entirely possible if you told a lot of people to eat cabbage when cabbage actually is possibly very bad for their heights.
Science, man.
Okay.
No, I think there's really nothing except hoping that you are clever enough to have thought of enough to save you from the possibility of some additional model that comes along. There are situations in which you can show that it's more or less likely that there's another model that will come along. I fit this as well as it can be fit kind of thing. But, you really can never guard against a sufficiently clever person coming along later and saying, I've got another model that fits the data just as well or even better. I mean, that's why we're all here and excited. Otherwise, we just run and stand all day, right? Like, that's not the fun part. The fun part is the just so stories. That's the science. Yeah. Is that satisfying? Dissatisfying?
I was kind of hoping you might suggest something.
Well, we'll talk. I mean, we've sort of been talking implicitly about model checking. We'll talk about model comparison. You know the things I'm going to say because we talk all the time. But there are some things. But in the end, fundamentally, there is no surefire protection. Okay. What did I call that? I called it EX1 data, right? Oh, good. Oh, look. Okay, so fantastic. So it produced an M and a B again. It produced a sigma, which now is interpreted as the scatter about the line. Right? These unmodeled effects that mean your data, the real true values don't lie perfectly on the line. And it produced a Y true. So let's just look, Yeah, that's right. Y true is all over the map. But of course we know that because X true is all over the map. So we expect to see a spread of these things. There's no requirement that they overlap. Sigma here is, okay, well, whatever. It scatters by of order or whatever that is, 50. I don't know why Stan compresses these plots on the R Stan. If you use R, no astronomers actually use R. They probably should. But anyway, if you use R, which is another stats modeling program that can also call Stan, the plots look prettier. Okay, so M and B are whatever they are. Let's copy our plotting code and let's have a look. Okay, we're no longer scaling the errors up. Oh, and we don't want to actually plot, yeah, we don't want to plot the true things with no scatter. We want to plot the x's, and then we want to plot what did I do wrong? Oh, yeah, thank you. Okay, somewhere I did something crazy.
Table 1.
Oops, thank you. There we go. Okay, beautiful. So the line scatters more, but now it's kind of hard to see. The green points here, you can just barely detect them being slightly away from the measurement. This model is much friendlier to our observer friends. Effectively, what it's doing here is it's saying, well, there's still a linear relationship, but when I have something like this where the observer has a tiny error bar and is 5 sigma away from the linear relationship, that's an indication that the intrinsic scatter must be pretty big, and this point just scattered down here. When I have something that's either got a bigger error bar, that one's hard, the one up top there, when it has a bigger observational error bar, the observers are more uncertain, then I will let the model sort of pull it towards the line, right? That green dot is below the black dot, and in fact you can't see it, but I bet a lot of money that the green error bar is smaller than the black error bar, because it's averaging the model observations with, it's averaging the model prediction with the observational uncertainty and obtaining something that's better than either one alone. Does that make sense to everybody?
So should we actually do chi-square test on residuals? I mean, in general, I guess that's sort of the one thing we can obviously check for
so
as a way of
in either this model or with Ilya's idiot factor, where you let this scatter scale, the chi-squared on the residuals will be just with perfect distribution. Because you are adjusting the size of the scatter so that the residuals come out to be Gaussian.
I'm not convinced, for example,
they don't have to be a perfect distribution, I guess.
Because you have, actually, if you look at your data, the ones that are furthest away, some of those points have the smallest error bars, and so my model wouldn't be enough to appropriately correct things. I bet you my distribution of
yeah, okay, I'm sorry.
Right.
What I should have said, your chi-squared value will be 1. Your distribution will be off.
Exactly. So that's what I'm asking. Should we do it as, there are frequent this chi-squared test. Should we actually, so do you suggest as a matter of principle we should apply these things?
It's a totally reasonable thing to apply, yeah. And in fact, what I should have said is you should look at the distribution of chi-squared, not the value. This will basically tune the sigmas until the chi-squared equals 1, but it may be heavy tailed one side or the other, indicating outliers doing something special. Okay. So in principle, I have 5 more minutes on the original schedule. How much can that slip?
You have 25 minutes left. You started at 2:45. You still have the full time.
Okay. Can we fit the whole data set with this model? There were 4 bad points in it, right? Can we fit the whole data set and see that it goes wrong and then fix it all in 25 minutes? I think we can do that. Okay.
You're the driving force.
Yeah. So, hang on. So now, what we're going to do is we're going to just change the data, right? In the old data, we were just using starting at 4. And in the new data, we'll just use everything. Okay, so we got a new fit. Okay, let's see what that implies. So let's copy our plotting code. Let's see if we can plot both of them on top of each other. So in this case, we use all the data. Okay, so the old data is the blue line. The new data is the green line. The old y-trues are the green dots. You know what? Let's change those colors. Let's make it more interpretable. So the old y-trues, we're going to make them blue. And the new y-trues, we're going to make them green. For the colorblind. There we go. Okay, so first off, the blue thing doesn't fit 1, 2, 3, those 4 data points. When we do fit them, you can see that they have just ridiculously tiny error bars, which means they have a lot of power. They want to pull the line there, right? If you continue this blue line, it misses this point by something like 100 sigma. When was the last time 100 sigma happened in life? It never happened. Right? 100 sigma means something is wrong. Okay? So, the green line pulls down in slope to try to match these points, but just basically screws everything up. Now, interestingly, the green predictions and the blue predictions really aren't all that different. The y-trues are quite close to each other, and that's just because our observer friends are really good, right? These are tiny error bars. So what you'll discover, I didn't look at it, but I bet the model scatter on green is huge. Green is basically saying, this is a flat line, and it scatters up and down across the whole box. Okay? Does that make sense? Now, outliers can screw you when you're fitting a line, or anywhere else. What should we do? Well, if you were, and now let's think like an observer, if you saw this data point in collection with all the rest of those, you'd do what Enrico said at the beginning, right? The same thing that they said to do. You'd say these 4 data points are outliers, and you'd get rid of them. Okay, the bats flew over my telescope, or the seeing was bad, or it's a different object and I didn't realize it, or, whatever, right? There would be a reason why those guys are there and everybody else is on the line. So why don't we put that into our just so story? So our just so story now is, for any given data point, either it follows this line with scatter, or it's basically just random.
Or your models or something like that, like an S.
Yeah, no, that's true. We could put in some
Because
kind
the
of...
outliers are on
But
the
I mean,
edge, which is always dangerous.
that outlier, right, it's right in with those guys. So either the model's doing, some kind of curve or going, woo!
All the physics.
This is time. That's a transient.
New physics.
Yeah, no, exactly. So these could, if it's 100 sigma, it could be an indicator of new physics. But for now, let's pretend it's a mistake. Right?
That's
So
what astronomers do all the time.
that's right. It's a mistake. So either, yeah.
So you can say it's a mistake, but let's say you have 20 good data points and 3 outliers. What if you had 2,000 good data points and 300 outliers? That would be too many mistakes, though.
Then they're not
I don't know. Have you ever looked at the Kepler catalog? No, actually, I ask this in seriousness, okay? You look at Kepler, fantastic planet discovery, right? You know what I'm talking about. They have a catalog. It's got 5,000 or 6,000 objects in it. Now, there's a disposition column, okay? Now, some of them it says false positive. It was in the original catalog. We've subsequently discovered it's not a planet, but we leave it here and just tag it bad. Many of them are disposed as candidates, and up to 10%, sometimes more, depending on what the parameters are, of those are known to be crap. You don't know which ones, but you know that your contamination is of order 10%. So that's, you said 2,300, so I guess that's a little worse than 10%, but, the Kepler guys are pretty awesome. So it's not true that, a 10% contamination means you should quit. It might be okay. Depends, again, it depends on the science question you're answering. It depends on what the bad means about your instrument. I agree that if it's your bathroom scale, if 10% of the time it returns 300 kilograms, it's probably a bad scale. But if it's something like Kepler, where there's lots of possible non-planetary sources that trick you, then a 10% contamination rate can be world-leading and perfectly fine for getting your science done. So this is, again, we do science, we don't do math for a reason. You have to think about what it says in the context of the just so story. Okay, in this kind of model, there's two ways we could treat this. We could either give each dot here a little flag. Good data, bad data, good data, bad data. Right? We've now expanded our parameter space. There's 20 data points there. Okay? I think there's 20. I hope there's 20 data points. So now there's, 0, 1 to the 20th power is an additional part of our parameters. Good, bad, and we could sample in that, just not with Stan. Stan can't do discrete things. It can't flip those bits to good and bad.
Well, you can give them Ilya factors to
We could
just
give
those four.
we could give Ilya factors to those four. So we could take those four specially and blow up their errors. Or, in a more systematic thing, what about this one?
It doesn't fit, let's throw it out.
That point, well, I don't like it, right? It's way below the line. It's really increasing our intrinsic scatter a lot. So if we got rid of that, the intrinsic scatter would be smaller, right?
Like the Hubble law.
Yeah, what about this one? That one's kind of crappy too. So you can see, pretty soon, what we're coming up with here are procedures. And read the paper that's the Bible. Hogg will just rant, and he's right, about procedures. Okay? I like just so stories that lead to mathematically quantifiable likelihoods. I'm happy if they're wishy-washy and fuzzy and not real. Okay, don't confuse the map for the territory. Your model doesn't have to be real, but it should be specified. And these procedures of I want to get rid of that one, I want to put a factor on that one, I want to put a factor, those aren't specified. It looks hinky to me. So what I suggest is we say either things come from the line or they come from a Gaussian in Y, completely independent of X. Really, there's only 4 data points there that sort of scatter. So let's just fit a Gaussian with a mean and a standard deviation in the vertical direction to those. Okay? That means that the probability distribution just to distinguish these two sigmas. The probability distribution is with probability A, which is some number that's probably about 15 out of 20. With probability A, Y true comes from our line with some intrinsic scatter. And with probability B, it comes from some just random Gaussian with some mean and standard deviation that has diddly to do with the X value. And so we'll introduce 3 new parameters. A is the reliability factor. It's great for naming and shaming. It's the reliability factor. Mu is this sort of junk thing that's just the mean value of all the outlier points, and sigma is the scatter of all the outlier points. Okay.
So look, this looks on the surface nicer than a procedure because you've described this. However, the difficulty is you pick this distribution from which you're sampling wise after looking at the data.
Yep.
And oftentimes you can only do this after looking at the data for the very simple reason that if you're doing some astronomical survey, maybe you didn't guess before launching Kepler that there would be these 10% outliers due to binaries that look like exoplanet systems or whatever it might be, and so you don't expect this contamination population. And now, you've written down a nice pretty model, but it's still actually based on the data. Your model is based on the data, which is fine.
Yep.
I mean, it's perfectly fine to write models based on data, but let's not confuse these with sort of a priori physical models we're trying to fit, right? It's still a kind of procedure, right? So is it really that much better?
It is better because it tells you, if you would like to say, what's the probability that this point is bad? The kind of question you'd want to ask in a principled way is not does it mess up my slope, but overall, what fraction of points are bad? So how likely is it that any particular one is crappy? Weighed against, does it lie right on my model? That's probably good. Is it really far off? That's probably bad. Some mix in between them. And if you don't have this kind of probabilistic story, it's very hard to work out a consistent weight, right? So people often do sigma clipping, for example, right? I've got this preliminary fit to my line. Anything that's more than 5 sigma from it, I just throw it out because it's contaminated. And in many cases that works, but in other cases that ends up throwing away all your data. You iterate that procedure and you're left with nothing. How can you guarantee that that's not going to happen? Well, this doesn't ever leave you with nothing because it's interpretable as a just so story. Okay. And I agree, I've done this after looking at the data, but I think, at some level, I guess what I'm reiterating here and what is cast in different language in Hogg's paper is really science is about telling just so stories. Okay, so, and then we can argue over whose is more convincing and whose fits the data, all of those things. But if you don't have a story, you're not really doing science.
But you're also parameterizing your ignorance in a consistent way.
That's right. The key point here is consistent. You're not,
Choosing peaking.
Yeah. Now, frequentists here are falling over dead because I've looked at my data and I've made up a model and the frequency properties of this thing are horrible and so on, but I'm not a frequentist and so I'm not fussed. But, you have to be careful. If you live in that statistical universe, then this can be quite dangerous once you've looked at your data and you have to ask lots of other questions. It's a bit tricky. But that's not the universe that I'm living in for these lectures. So I do inhabit it occasionally.
I mean, I think you can always say that as long as your model has some predictive power, it doesn't matter even whether it has any physical meaning at all, right? That's not enough.
Well, but if you want confidence bands on A, for example, you have to ask, what other sorts of data could I have gotten, and then you have to, yeah. Okay, so let's fix this. We're going to take our linear model scatter and turn it into linear model scatter outlier. Okay, so we said now we're going to introduce a new parameter.
Not working in the right file.
Oh, thank you. Beautiful.
Yes. Less painful.
A, which is between 0 and 1, right? Either they're all good or none of them are good, but you can have minus 2 of them that are good. Now we want a mu. Now I'll explain why I'm writing it in this funny way in a minute. Okay, so Stan has a function that's called log mix. This is formally called a mixture model because we're saying something is either A or it's B. It's either type 1 or it's type 2. So to write that in Stan, you just say, so target here represents this density function that we're trying to sample from. It's actually the log of that density function. So you can either influence the density function by writing y as a squiggle, which is a more intuitive thing for people who are used to statistics, or you can explicitly increment the log probability. we're just going to explicitly increment the log probability. Okay? Oops, let's make sure we do that too. I think that should work good. And, log mix just takes the log of this and the log of that and adds them together with a and 1 minus a in a way that's numerically stable and convenient. Okay, and other than that, our outlier model hasn't changed, right? Y's true when they come from the real thing, have the same shape, etc., etc. So let's compile that and see what we get. Probably I made some higher, but okay, model outliers. Oh. Yeah, that's right, sorry. Yep, y true. And that's it, right? Thanks for everybody who's following along in the audience. Good. Okay, there we go. Does everybody understand what I did there? Because for every single observation, this is the probability distribution. So I'm adding together the logs, which is just multiplying together all the probabilities, because the observations are... Everybody on board? Yeah, that's right. That's right, hopefully. We'll see what kind of, this could return reasonable results because it works. It could return unreasonable results because it doesn't work, and it could not work because I messed it up. But I think with enough eyes on the problem. I hope also, on a meta level, see, I'm filling time here while this compiles. I hope on a meta level, this is serving as sort of an ad for things like Stan. For people who, how many people use MC? I've used MC a lot. I really like MC. Imagine coding these models in MC. Okay, things that are like bounded between 0 and 1. Oh, you have to remember to check that, right? The description here, particularly for this sort of, this is exploratory data analysis, right? We're fitting, we're looking, we're fitting, we're looking, we're fitting, we're looking. The exploratory data analysis power of something that lets you really concisely describe your model is just phenomenal compared to having to code everything up. That advantage falls apart, as the models get more and more and more and more complex. By the time you're doing integrals over co-moving distance in cosmology or something, Stan starts to look less and less attractive. But for this simple stuff, it's really powerful. What happened? Oops, I misspelled it. What did I call that data? Data bad. Ooh. I was going to say this takes a long time to run, but it actually doesn't. Oop. Where? I misspelled the model outliers, but fit outliers I didn't. Oh, it's not going to plot. Hang on. Yeah, there we go. Uh-oh. Okay, so this is a good example. So it was unable to plot things. I wonder why. Well, if you look here, what did sigma return? And sigma just ran away. What happened? Well, if sigma gets really, really, really big, then this here, right, this model gets basically flat, and this probability just shrinks and shrinks and shrinks and shrinks and shrinks, right? So everything goes, that's saying A then has to be 1. And you get the bad fit you got before. But that's not ruled out with infinite improbability, right? So as sigma goes to infinity, this term just goes away, and we're back to the fit we had before, and so it just runs off to infinity. I guess we better impose a prior on sigma.
Sigma's the one in the other bit of the model.
Oh. Sigma's, I guess it went the other. I guess you could make the same argument, though, as this sigma goes to infinity, right? Yeah, either way, it's one of these sigmas, and it'll actually just be a matter of which one the sampler ran in first. Yeah. Okay, so this is a good example of exploratory data analysis. So let's say this is cheating a little bit, but let's just say we would like the outlier sigma to be log normally distributed sort of on the order of the standard deviation of y's. Okay, right? If it's much bigger than the total scatter of y's, there's no point. It's just saying there's a flat background distribution, right?
Putting a bound on A.
What was that? Yeah, you're putting a bound on how low A can possibly go by doing that. And let's do the same thing for the other sigma, just to make sure everything stays. Nope.
But if you added another term, like times e to the minus sigma, so the bigger it is, the less important it will be.
You could certainly add that. So I could give it, instead of a log normal, which doesn't like it to be small or large, I could put in just an exponential, say, which is basically not mattering until it gets to some scale. Stan has an exponential distribution as well. Let's do that. Problem is I need to look up the exponential. I don't know whether this is the rate constant or the inverse rate constant. So let's see. Oh, no, I did this. It's not so helpful. Here we go, positive continuous distributions. Okay, it's the rate constant. So if we want the probability to fall off when sigma gets bigger than, now if we look at our data, it scatters by a few hundred. If we want the probability to fall off when sigma gets bigger than a few hundred, we should set that to 0.005, let's say. There. And in terms of the scatter, let's make that smaller. So we believe that there's a tiny scatter about our line, and then the outliers are really big. Okay, so the scatter about the line starts to cut off when it's of order 20. All right, Anilia's telling me I have 3 minutes, which is perfect time to check the fit. Now I should say, I've seen this done in a few papers, this sort of outlier rejection. But at this point, in terms of standard practice in astronomy, we're really maybe a little bit past the forefront. Okay, not very many people, like if you look, for example, at the recent Rees et al. Paper about, fitting H0 from supernova data, they don't do outlier rejection by soaking them up with a statistical model. They do outlier rejection by, nope, yep, these are good. So, we're pushing state of the art here in an hour and a half. Okay. Whoa! All right. Well, that blew up. Okay, I'll post the completed code tonight. I think we're going to have to diagnose why this thing's running off to infinity unless somebody can see right away. But I'll take the last 5 minutes. Are there questions? Yeah, Zohar?
So those posterior distributions on the M and V that we were looking at before, if those were, ill-behaved looking, or they had, they were bimodal or
bumps or something.
Yeah, would that tell us anything that we should?
So, most likely, if you look, say, at this posterior distribution, right, and saw it was like double peaked, I would immediately check those chains, because in fact, Stan runs 4 separate fits, completely statistically independent of each other, and then mashes them together. And the most common cause of bimodality is that 1 or 2 of those fits latched on to one value of M, and the others latched onto the other. And that is indicative of a failure. There's nothing you can trust about your results at that point. Stan has failed to sample this function. You must try again. The usual recipe is to ask for more iterations, right? Stan's flying around in the probability space and it got stuck somewhere, so just make it fly longer.
So I mean, actually, not even in terms of the stand, but in terms of your actual posterior, once you
So if you really saw like all four, like it looked like this, except they were sort of mixing between the modes or something. If you see that, then you really have two solutions. And you can, then natural questions to ask are what fraction of the posterior lives in this solution versus that one? How likely is it the line's flat versus steep? Then that's real. This really has two peaks. And you should be able to see when you plot these two lines, you should look at them and go, yeah, okay, I see. I can kind of fit it well with that. I can kind of fit it well with that. And I don't really know which one is better. And if you can tell that consistent story, then that's what your model's saying. I don't know what the slope is. It could be this or that. It can't be that. And then, when you write your paper, you can't really do m equals m naught plus or minus sigma m because you're kind of lying. You've got to find some way to describe what's really happening with the two peaks. That happens. Gravitational wave data analysis, we get multiple peaks all the time. Yeah.
I don't know if you talked about this, we were a couple minutes late for the bikes, but what kind of sampling procedure does Stan use?
It's a Hamiltonian Monte Carlo, if that means anything to you. We should sit down over a drink, and I can tell you all about it at great length, but it's several lectures in and of itself. Yeah.
It's something I need to check. So, whenever I've heard the phrase "just so story" in the past, it's had a negative connotation.
Yeah.
Are you using it in the same sense?
No.
No.
I'm using it to mean something you might think is negative, but is actually useful. So it sounds wishy-washy, right? And it's certainly not reality. But I'm not, I'm not trying to drag in all the colonial associations, which, I understand that's there. But it's a simple story that hopefully captures the elements of reality that you care about, so that you can fit the data.
Okay.
I said this before, there's a catchphrase, don't confuse the map with the territory. Right? You hope you have captured the important parts, the features in your data that matter for whatever model you're fitting or whatever physics you're doing. And you have to discard the rest, because you can't really fully model the whole thing, even in simple experiments like the backward scale. Imagine building a real mechanical model of your backward scale. No, it's not.
Can you give us your favorite example of two just so stories that fit the data almost equally well?
Yeah. GW 150914 was two Schwarzschild black holes merging. GW 150914 was two Kerr black holes merging with non-zero spins. Those are two just so stories that both fit the data basically identically. Yeah.
Could you speak a bit to that frequentist criticism of this whole approach, where you have to specify prior?
So honestly, in the major points, this is not terribly different from frequentism. There's a difference in it. Here, there's a prior. So here, we're imagining we've got the data we've got, right? The data are fixed, and we're asking about a distribution over our parameters. And we're thinking of it as our uncertain knowledge of the parameters, right? I don't know what they are. I'd like to understand how uncertain I am. Or if you like, I'd like something that gives me, good bets when I go to God's betting window and have to place, money on black holes, right? What are their masses? The frequentist approach says the opposite thing. There's a true, those black holes had a mass, right? Whatever it was. I don't know what it is, but they had a mass. Data, though, are random, right? I could imagine detecting 150914, hundreds of times, and each time I get different data because the IFO is rumbling differently. So then it says, well, let's try different values of the mass, and let's ask, at some point, for certain choices of mass, the data I actually got are wildly improbable compared to other choices of the mass. So let's come up with a procedure where I sort of draw bounds in mass space so that, 95% of the time when I get some data, I follow this procedure, I get bounds, and the true value is in there. So it's imagining, it's sort of asking, that's where frequentism comes from. You're performing the experiment repeatedly, following some procedure, getting, some kind of, they call it confidence interval on the parameter. That can work, and in fact, both procedures are likelihood dominated, right? This is the part that matters for both of them. The prior is different. Prior happens in the Bayesian framework. It doesn't happen in the frequentist framework. But the likelihood function usually dominates the prior. Whatever the likelihood function is, we evaluated at each data point. There's 20 data points. You multiply together 20 factors of the likelihood and then one prior.
Well,
So, yeah.
sorry to cut you short, but I think we need to leave it at
Okay.
that.
So anyway, yeah, they both use the likelihood. Frequentists are just looking at sort of repeated, many experiments. Give me something that I usually not wrong.
Yeah, so we're going to start again at 4:40 in 20 minutes. And then hopefully that means we can still have enough time today, and people will still be awake for the part of the presentation. So if you're presenting your project, make sure you're here on time. If you're listening to the project, also make sure you're here on time. 20 minutes.
And I'm very happy for people to come up to me and tell me they liked it or hated it, or email me or whatever.
I gotta say, I want to reject